So thank you for the introduction. So I'm Takashi from NTT, and today I will talk about verifiable content advantage with our structure. And this is a joint work with Mark Zhandry from NTT Research. So what is content advantage? It is a demonstration that quantum computers outperform classical computers, at least for some tasks. And here are several famous examples of quantum advantage. For example, probably one of the most famous examples is the short algorithm that solves factoring and discrete log problem in quantum polynomial time. And we believe that that is difficult for classical computers to solve in polynomial time. So this is a quantum advantage. And another example is robot search algorithm that solve general NP search problem quadratically faster than the best classical algorithm. And yet another example of a slightly different flavor is some sampling task like boson sampling or random search sampling, where the task is to sample a classical string according to some specified string. And recently there were several implementation attempts for this kind of sampling-based approach of quantum advantage. And especially in this work, we focus on quantum advantage with these two properties, super polynomial speed ups and classical verifiability. So super polynomial speed ups mean that the ratio between the time complexity of the quantum algorithm and the best classical algorithm grows super polynomially in the size of problem instance. And the classical verifiability means that once the solution to the problem is given by the quantum computer, then it is easy to verify that the solution is actually the valid solution to the problem. And in many practical scenarios, when useful problems are often classically verifiable, or in other words, they are NP problems. So this is a very important class to study. And from this perspective, we can categorize this example like this. For sure, this satisfies both, because we believe that there is no classical polynomial time algorithm for factoring or discrete log, but we have quantum polynomial time algorithm. And also, it is easy to verify that the solution to factoring or discrete log is correct. And on the other hand, Grover only satisfies classical verifiability because we can check the solution is correct if that is given, but that only gives quadratic speed ups. That is just a polynomial speed ups. And for sampling, there are several examples of sampling tasks for which we have evidence of super polynomial speed ups, but we don't know how to classically verify that because even if we are given some string that is supposed to be sampled from some distribution, basically there's no way to check that is rarely sampled from that distribution. And okay, and so especially in this work, we focus on this kind of quantum advantage, and simply I say such quantum advantage, verifiable quantum advantage. And so how to prove verifiable quantum advantage? And first, I would like to remark that it is hopeless to unconditionally prove the existence of even non-verifiable quantum advantage. And this is because if we can do that, then that automatically implies P not equals to P space, which is a major open problem in complexity theory. So this is very difficult. So usually for proving some result about quantum advantage, we rely on either of the following approaches. First is to rely on some computational assumptions. For example, for Shor's algorithm, we already know that we have quantum polynomial time algorithm for factoring. And for getting the quantum advantage, we have to assume that the factoring is very hard for classical computers. And the second approach is oracle separations. So in this setting, we consider some oracle that is a black box that computes some functions. And the typical example of this setting is the Simon's algorithm. In this algorithm, we are given some oracle that computes some periodic function, and we have an efficient quantum algorithm to find the period given the quantum black box access to the oracle. But we can show that that is not possible for classical computers. And the nice feature of oracle-based setting is that it is usually easier to give the classical lower bound And so, for example, for period defining problem, we can show the classical lower bound unconditionally in the oracle-based setting. And in the real world, we don't have oracle, but usually such an oracle-based separation have been considered as evidence for the separation in the real world. So we have these two approaches. And let's see the examples of verifiable quantum advantage in these approaches. So for the assumption-based setting, as I already mentioned, Shor's algorithm gives a verifiable quantum advantage. And another example is Pell's equation problem by Hargren. And also, here is another example of a different flavor based on LWE problem, which is some problem related to lattice problems. So the interesting feature of this protocol is that we believe that the LWE problem is hard, even against quantum computers. But assuming the hardness of LWE problem, we can construct, they construct the interactive protocol that is some interactive task that is easy for quantum computer, but difficult for classical computer. And so such a even quantumly hard problem gives the quantum advantage is an interesting result. And for oracle-based setting, there are several results about verifiable quantum advantage as well, like recursive Fourier sampling by Bernstein-Baziani, period finding by Simon, as I already mentioned, and also Verdi trees by Child et al. And here I make the following observation. So in the assumption-based setting, all these assumptions or their closely related variants can be used to construct public key encryption. And on the other hand, for the oracle-based setting, we can see that oracles that appear in this example are all based on some structured oracles. For example, you can see that for period finding problem where we assume the periodic oracle. And actually, this doesn't seem to be a coincidence, and we have the following folklore. The folklore is that public key encryption requires structure in some sense, and this is just folklore, and I don't have any formal statement. But based on this folklore, I ask the following question. The question is there verifiable quantum advantage without structure? And put it differently and more concretely, this means the following. For the assumption-based setting, can we give verifiable quantum advantage without assuming public key encryption? And for the oracle-based setting, can we give verifiable quantum advantage based on structureless oracles? Or in other words, random oracles that are oracles that simply compute random functions. And this is our main question. And our main result is that we resolve the question affirmatively. And specifically, in the oracle-based setting, we give the first verifiable quantum advantage relative to random oracles. And moreover, this is non-interactive and publicly verifiable. So this means that we have super polynomial quantum speed apps for an NP search problem. And this can be used to also obtain the result in the assumption-based setting. So simply, we replace random oracles with some real-world cryptographic hash function. Then we get verifiable quantum advantage based on hash functions. And this is justified by some heuristic called random oracle heuristics that is often used in cryptography. So this means that if we replace random oracles with some well-designed cryptographic hash functions, then that still should work. And based on these heuristics, we also obtain assumption-based quantum, verifiable quantum advantage. And so the main takeaway message is this. Structure is not necessary for verifiable quantum advantage. So by using some picture, so our result is illustrated like this. So we can consider the following three properties for quantum advantage: classical verifiability, super polynomial speed apps, and without structure property. And if we give app without structure, then we can simply use Shor's algorithm for factoring or discrete log. And if we give app super polynomial speed apps, then we can use Grover. And if we give app classical verifiability, then some sort of sampling task suffice. but ours is the first to satisfy all of them simultaneously. And here, let me mention a related conjecture by Aronson and Ambanis. And they, under some mathematical conjecture, prove that the random oracles are not useful for showing super polynomial quantum speedups for decision problems. And that paper was titled The Need for Structure in Quantum Speedups. But as I just explained, that we demonstrated quantum speedups without structure. So does that mean that we refute the Aronson-Ambanis conjecture? And actually, it is not the case because we consider some search problems, but the Aronson-Ambanis conjecture only consider decision problems. So our results suggest the important difference between the search problem and the decision problems, which are sometimes overlooked. And I'd like to mention cryptographic implication. So in cryptography, as I already mentioned, there is a heuristic called random oracle heuristics, which means that the well-designed cryptographic hash functions can be regarded as random oracles in the security proofs. And this has been used for analyzing many practical cryptographic protocols. And the model is described like this. And so random oracle is given the input x and computes some function h of x for randomly chosen function, random function h. And yeah, this is a random oracle model. But in 2011, Bonnet et al. Pointed out that this model is not sufficient for analyzing security against quantum computers. The reason is that if you have a quantum computer, you can evaluate hash functions in superposition. On the other hand, this oracle only gives classical access to the random function. So this doesn't capture quantum evaluation of random oracle, I mean a hash function. And considering this issue, they proposed the new model called the quantum random oracle model. Basically, this is the same as the random oracle model, except that now one can access the oracle in superposition. And now this is the de facto standard model for analyzing practical cryptographic protocols that is supposed to be secure against quantum computers. And there have been a lot of work about the security proofs in this model. On the other hand, the following very fundamental open problem was left by the Bonnet et al. Work that proposed the quantum random model. The open problem was, can we separate the random oracle model and the quantum random oracle model? So this means that is there any cryptographic protocol that is secure in the random oracle model, but insecure in the quantum random oracle model? And this open problem itself was recently solved by our previous work and also concurrent work by Zhang et al. And in those works, we gave some examples of digital signatures and public key encryption schemes that were secure in the random oracle model, but insecure in the quantum random oracle model, assuming the hardness of the LWE problem. And this was the previous result. And in this work, we can improve this state of the art as an immediate corollary of our main result. So as a corollary of our results, we improve the following two perspectives. First, we can remove the LWE assumption, the hardness of LWE, and we now get unconditional separations between random oracle model and quantum random oracle model. Second, we can extend the separation to one-way functions and the collision-resistant hashes that are more fundamental primitives than digital signatures and public encryption. And so our results confirm that for ensuring security against quantum computers, we have to actually give security proof in the quantum random oracle model rather than in the random oracle model. And we also get some additional result about proofs of randomness. So this is a protocol between quantum prover and classical verifier, where the classical verifier, after the interaction with the quantum computer, finally outputs some acceptance or rejection symbol, and also some classical string S. And we require the following two properties. As completeness, if the protocol is run honestly, then the verifier accepts with probability almost equal to 1. And as soundness, conditioned on acceptance, the classical string S should be almost uniformly distributed. So this can be seen as a protocol to delegate the generation of the random string to untrusted quantum computers in a verifiable manner. And we construct such a proof of randomness protocol in the quantum random numerical model, assuming that the Aronson unbiased conjecture is true. And the previous construction of such a protocol was based on LWE, which is some structured assumption. So ours is the first protocol to construct proofs of randomness without structure. Okay, so from now, I would like to move on to more technical part. So recall that our main result is to construct some problem that is easy for quantum computers, but difficult for classical computers. And the problem is described here. So C is some linear code over a finite field, FQ, with the length n. In other words, C is just a linear subspace of FQ to the n. And the concrete instantiation of C will be mentioned later. And we also use n random oracles, hi, for each I from 1 to n. And for each I, hi is a function from FQ to 0, 1. So it has 1-bit output random function. And the problem is described here. The problem is to find a vector x that satisfies the following two simultaneously. First, it should belong to C, the linear code C. And second, hi of xi equal to 1 for each I from 1 to n. And recall that hi has a 1-bit output, so the output should be 0 or 1, but the second condition requires that it should be all 1. And we have to show the two properties. The completeness means that we have an efficient quantum algorithm that solves this problem efficiently with probability almost equal to 1. And as soundness, we have to show that for any efficient classical algorithm, A outputs a valid answer with probability almost equal to 0. And I remarked that we actually only need to restrict the number of queries by A. I mean, number of classical queries by A by some polynomial function. And we don't need to restrict the actual computational power of A. And I also remarked that here H means the shorthand for the n random oracles, H1 to Hn. And so we have to prove these two properties, and let's see them one by one. So let me start by explaining the intuition for soundness, why this problem is difficult for classical computers. So the first observation is that it's easy to find X that satisfies either of 1 or 2. For 1, it's very trivial. So if we are given a description of the code C, or in other words, generator matrix of C, then it's trivial to find an element of C. And for 2, this is less trivial, but this is still easy, and this can be done as follows. For each I from 1 to n, do the following. Randomly pick xi from fq, and check if hi of xi equal to 1. If it holds, then go to the next I. And otherwise, try the same procedure again until it succeeds. And finally, we get x1 to xn, and so we concatenate them and get x. And then we can see that x obtained by this procedure satisfies condition 2, because we choose xi so that hi of xi equals to 1. Moreover, for each I, in the loop, for each I, the expected number of trier is 2, because the probability that we have hi of xi equal to 1 is 1/2. So in expectation, we only need to repeat this twice. And so the whole procedure is also run in polynomial time. So we can see that it's easy to find x that satisfies either 1 or 2. But it seems difficult to find x that satisfies both. For example, if we first pick x that satisfies 1 by using the trivial way, then the probability that x satisfies condition 2 would be very small, because if we first fix x, then the probability that hi of xi equals to 1 is 1/2. And we have any conditions, so the probability that this holds for all I is 2 to the power of minus n, which is very small. And on the other hand, if we first pick some x that satisfies 2, then the probability that this x satisfies 1 is also very small, especially because we set the linear code C to be sparse. In other words, the fraction of the code word in the whole space is very small. And so, as you can see from this slide, so at least the trivial ways of solving this problem doesn't work classically. But of course, for proving soundness, we have to show that this problem cannot be solved by any classical algorithms. And let me briefly explain how to prove that. So this is a proof sketch. So let A be the classical algorithm, and for each I, let Si be the set of queries to random oracle Hi. And we also make some simplifying assumption that A's final output x star, or which is x1 star to xn star, should be already queried to the corresponding random oracle. That is, for each I, xi star must be queried to hi before outputting the final output. And this is without loss of generality, because otherwise we can modify the algorithm to do so. And so we have the assumption of x star is in S1 times S2 times 2 times Sn. And moreover, when the final out x star is a valid answer, then it must satisfy condition 1. Therefore, it must, the x star must belong to the intersection of C and this query set. And here we consider any fixed element x in this intersection. And then, for each fixed x, the probability that x become a valid answer is 2 to the power of minus n over the random choice of h. The reason is that for any fixed x, the probability that the second condition is satisfied 2 to the power of minus n. And so, if we can show this inequality, so the size of this intersection is more than 2 to the n times some negligible function in n, then the union bound gives the following. So probability that the final output is the right answer is negligible. So it suffices to choose the linear code C so that this inequality is satisfied for any choice of polynomial size S1 to Sn. And so how to do that? And we found, interestingly, we found that this property is just a special case of some well-studied property called list recoverability in the classical error correcting code. So if we assume that C satisfies some sort of list recoverability under some parameter, then we can automatically have this property. And so the soundness holds. And here I made, so this proof sketch is a little bit oversimplified. And the reason is that we first fix the query set Si and then consider the randomness over H. But for the general algorithm A may make its queries depending on the response from the oracle. This means that S1 to Sn may depend on H. And so in this case, this argument doesn't work. But in the paper, we show that this similar analysis extends to the adaptive case. And basically, we only need to slightly strengthen this inequality, and that stronger version still follows from list recoverability. So the conclusion remains the same. So if we C satisfies some sort of list recoverability, then we have soundness for this problem. So next, I would like to move on to the completeness. So we want to construct a quantum algorithm that solves this problem. And let me start from some observation that is similar to the classical case. So it's easy to generate a uniform superposition over X that satisfies either of 1 or 2. And for 1, again, this is very easy. And because we are given the description of the linear code C, so of course, it is easy to generate a uniform superposition over the element of C. And for 2, this is also similar to the classical sampling algorithm, which I already explained. So this is done as follows. For each I from 1 to n, I do the following. First, generate a uniform superposition over FQ, and coherently evaluate the random function hi to get this state. And then we measure this second register. And if the outcome is 1, then the resulting state is this state. And then we go to the next I, and otherwise try the same procedure again. And finally, we output the tensor product of this state. And after finishing this procedure, we can easily see that this is a uniform superposition over all X that satisfies the condition 2, because for each I, this state is a uniform superposition over xi that satisfies this inequality, so we can simply concatenate them to get this state. And so let me rephrase what I just mentioned, I just explained. So let V and W be indicator functions for conditions 1 and 2. That is, V of x equal to 1 if and only if x satisfies the condition 1, and otherwise V of x is equal to 0. Similarly, W of x equal to 1 if and only if x satisfies condition 2, and otherwise W of x is equal to 0. And then what I just explained is that we can efficiently generate these superpositions. Their superpositions where the amplitude function on x is v and w, respectively. Because basically this is the superposition over x that satisfies 1, and this is the superposition over x that satisfies 2. And suppose that we can multiply these states in the following sense. So we suppose that we can multiply the amplitude function v and w to get this state where the amplitude function is now v times w. If this is possible, then we can simply measure this state to obtain the solution to this problem, because v of x times w of x is equal to 1. I mean the non-zero value, if and only if x satisfies 1 and 2 simultaneously. So this exactly means that x is a solution to this problem. Of course, such a multiplication of states is not always possible. So what we do is the following. First, we show a sufficient condition under which such a multiplication is possible. And this step is inspired by the work by Regis. And second, we show that this condition is satisfied in our case. And combining them, we can get the quantum algorithm that solves this problem efficiently. So let me explain how to do the multiplication of quantum states. So what we want to do is written here. We are given these two states, and we want to obtain this state. And the useful tool for achieving this is a theorem called convolution theorem. So this means the following. So suppose that we have this state which we want to construct. If we apply quantum Fourier transform to this state, then the resulting state is proportional to this state, where the amplitude function is v hat convolution w hat, where the v hat and w hat are discrete Fourier transform of v and w respectively, and the convolution, the definition of the convolution is written down here. And so, if we want to, of course, so because this is unitary, so if we apply the inverse quantum Fourier transform, then this go back to the original state. So if we want to construct this state, we only have to construct this state. And next, I will explain how to do that based on a Regis idea, and I will call it Regis trick. And so this is a template to construct this state, and this works as follows. First, we are given these two states, where the amplitude functions v and w respectively. And next, we apply the quantum Fourier transform to these states, and then we get a hat here for each state in the amplitude function. And then we add the first register value into the second register, and then the resulting state is this. And next, we uncompute x in the first register to get this state. And if we obtain this state, then we can simply apply the inverse quantum Fourier transform to get the desired state, as I explained. So this follows from the convolution theorem. And so the only non-trivial step in this template is this uncomputing step. And actually, such an uncomputation is not always possible. But this template says that if this uncomputation is possible, then such a multiplication of the states is also possible. So, okay, so this is a Regis trick. And let's move back to our problem, and let me briefly mention how to apply this trick to our problem. So as I already explained, v and w are indicator functions for the conditions 1 and 2 respectively. And as I also explained, it is easy to generate these superpositions. So by applying Regis trick, we can multiply this amplitude function to get this state. And then by measuring it, we obtain a valid answer to the problem. So the only non-trivial step to complete this algorithm is the uncomputing step that appears in the Regis trick. So here I write down what exactly means by the uncomputing step. So the task is the following. We are given this state, and we want to uncompute x in the first register. And recall that v and w are defined like this. And first, we reduce this uncomputing task to some classical decoding task as follows. First, we rely on the fact that Fourier transform of the indicator function for some linear code C is the indicator function for its dual code C pop, which is also a linear code. And so v hat is of the form of like this. And then we observe that for during this uncomputing task, it suffices to perform the following classical decoding task with high probability. The task is as follows. As setup, the x is randomly chosen from C pop, the dual code C pop, and y is chosen according to the probability density function w hat square. And we are given x plus y, and we should output x. And this can be seen as a decoding task because x is a code word of C pop, and y can be regarded as an error. And if this is possible, then by running this decoder for this state, and we apply this decoder on this input and add the XOR, the output of the decoder into the first register, and then we can uncompute this first register effectively. So now our task is reduced to this decoding task. And the decoding task is copied here. And for analyzing this task, we also have to know about what is the distribution of y, because that is error. And so let's analyze W. So the definition of W can be written like this. So W of Y1 to Yn equals to the product of Hi Yi for each I. This is just a definition, the rephrasing of the definition. And so its quantum Fourier transform is a product of Hi hat of Yi. And recall that each Hi is a random function. So the number of Yi such that Hi of Yi equal to 1 is almost Q/2. So according to the definition of discrete Fourier transform, we can show that about half of the weight of Hi hat square concentrates on 0. And moreover, the weights on non-zero values are almost equally distributed by symmetricity. And so by using this observation, the distribution of the error Y is almost as follows. For each I, Yi equals to 0 with probability 1/2, and otherwise, Yi is uniformly distributed over non-zero elements. And so it suffices if we have an efficient decoding algorithm for CPAP that can correct errors that come from this distribution. Here is some non-trivial issue. The issue is that, as you can see from the description of this error, the expected Hamming weight of the error Y is n/2. However, we know that there is an information theoretical bound about error correcting code that we cannot correct errors with Hamming weight larger than n/2 in the worst case. But remark that what we have to do is that average case decoding. That is, we already know the form of the error. The error comes from this specific form, and we only need to show that we have a decoding algorithm that works for this error with high probability. And in such a setting, we show that we can make use of the least decodability. So least decodability means that we have a decoder that outputs a list of candidates of the original code word that must contain the original code word. At first glance, such a list decoding is not useful for our purpose because we have to uniquely decode the original code word X. But what we showed is that thanks to the randomness of this error Y, even if we ran the list decoding algorithm, the resulting list contains only one element with high probability, so we can use list decodability for our purpose, and this resolves the problem. And the nice thing about list decodability is that it can overcome this information theoretical barrier about the worst case decoding, and so by using list decodable code, we can overcome the issue. So now I would like to mention how to choose the code C. So for soundness, we assume that C is least recoverable. And for completeness, we assume that C pop is least decodable under same choice of parameter. And we found that there is a code called folded Reed-Solomon code that satisfies both. So this is simply basically the same as the basic Reed-Solomon code, except that we regard several consecutive symbols as one symbol, and except that that is simply the same as Reed-Solomon code. And it is known that folded Reed-Solomon code is least recoverable, as shown by Grossfeld and Rivera. And also, its dual code is what is called general Reed-Solomon code. And it is known that it has efficient list decoder. And so, if we choose C to be folded Reed-Solomon code, then we can satisfy both. And of course, in the actual proof, we have to carefully choose the parameters. And but simply speaking, so we can use this code. And so now I would like to also explain our additional result about proof of randomness. So proof of randomness, as I already explained, this is a protocol to delegate the generation of uniform string to untrusted quantum computers. And let me explain how to do this using our idea. So, so we will construct proofs of randomness in the quantum random walker model, assuming that Aronson unbalanced conjecture is true. So let's recall what is Aronson unbalanced conjecture. So the informal statement is the following. For any A that makes Q quantum queries to random oracle and outputs 1 bit, there is a B that makes poly over Q classical queries to random oracle and simulates A. So this is the Aronson unbalanced conjecture. And the key observation is the following. Assuming that this conjecture is true, any quantum algorithm that solves our problem must be non-deterministic. This can be seen as follows. If there is a deterministic quantum algorithm that solves our problem, then the guessing each bit of the output of the quantum algorithm can be regarded as a sort of decision problem. Therefore, by applying the AA conjecture for each bit, we can classically simulate the algorithm in a bit-by-bit manner. But this means that we can solve the problem by using quantum computer. So this contradicts the soundness. The other result, there is no deterministic quantum algorithm that solves our problem. This means that if some quantum computer generates a valid answer to the problem, then that must have some amount of mean entropy. So our problem can be directly used as proofs of mean entropy. And then we can simply extract the true randomness from such a mean entropy by using classical randomness extraction techniques. Okay, so this is a summary of my talk. So we give the first verifiable quantum advantage with super polynomial speed apps relative to random oracles. And by using the random oracle heuristic, random oracles can be heuristically replaced with hash functions. And we also improved separations of the random oracle model and quantum random oracle model in cryptography as the immediate corollary of our main results. And we also give the proofs of randomness in the quantum random oracle model and the Aronson unbalanced conjecture. And finally, I would like to mention several open problems. And the first open problem is to give verifiable quantum advantage from standard assumptions in mini crypto, which is a hypothetical world where symmetric key crypto exists, but public key crypto doesn't exist. And the assumptions in mini crypto include one-way functions and collision-resistant hashes. And I know that there are several known constructions of verifiable quantum advantage from standard cryptographic primitives like claw-free trapdoor functions, quantum homomorphic encryption, or trapdoor permutations, but all of them rely on some sort of trapdoors, or in other words, public key crypto. But our work demonstrates that such a trapdoor or public key crypto is not inherent for obtaining verifiable quantum advantage. So it is an extremely interesting problem to study if it is possible to get verifiable quantum advantage from that kind of assumption in mini crypto. And the second open problem is an extension to classical verification of quantum computations, which is a protocol to verify that the computation result of quantum computation is correct by using classical computer. And the breakthrough work by Mahadev shows the first solution to this problem by using the quantum hardness of the LWE problem. And interestingly, that protocol was based on the earlier proofs of randomness protocol based on LWE problem. And now we have proofs of randomness based on quantum random walker model and AA conjecture. So there might be a hope to extend this to get classical verification of quantum computations in the quantum random walker model and probably with Aronson unbalanced conjecture. And the third open problem is if there is any useful application of our idea or our algorithm. So even though our result is theoretically interesting, the problem we consider itself is not very useful. So it will be very great if we can find any useful application of our algorithm. And finally, the final open problem, probably many people may be interested, is to improve concrete efficiency and to implement the protocol in the real world so that we can demonstrate the quantum advantage in a verifiable manner in the real world. And unfortunately, our current protocol, our current algorithm is not very practical, especially because we have to run the decoding algorithm of some linear code in superposition. But generally speaking, hash functions are much more efficient than public key crypto. And the only cryptographic component used in our problem is hash functions, and we don't need public key crypto. So this might be the first step to obtaining a very practical construction of verifiable quantum advantage verifiable quantum advantage with practical efficiency. And this is the end of my talk. Thank you for your attention.
Thanks, Takashi. So we have plenty of time for questions.
Thanks. Thanks for the very nice talk. So my question is in regards to classical verification of quantum computation. It seems like that as a first step might require showing some sort of quantum soundness for your protocol, so that in some sense, like any quantum device that succeeds in the protocol must be informally creating this uniform superposition over code words. So do you have any intuition about whether that can be shown, or even like showing, say, the proof of randomness without relying on the Aronson-Ambinus conjecture?
You mean without relying on Ambinus? So I would like to answer that. We are implicitly showing some sort of soundness against quantum adversaries by assuming Aronson-Ambinus conjecture, because at least we can show that there is some mean entropy for the output. But without Aronson-Ambinus conjecture, even for proofs of randomness, we have no idea.
Okay, thanks.
More question? Here.
Thank you very much for an excellent talk. I would like to ask you about those codes, because they should satisfy this double property of being least recoverable, both C and C complement. Are there many of them? Do you think one can generate in future more codes with such property?
Yeah. So I think there might be the possibility, but so we are not expert on the error coding code. But as far as we can tell, there is a very limited number of example of codes that satisfy least recoverability that is needed for our purpose, and the only example we could find is the 4D summon code. But of course, if there is some progress in the coding theory, then there might be more examples.
Thank you very much.
More question, Zhandry? So we still have time, so any question?
Hello. Yes, thank you for the nice talk and great work. I'm curious if you can share any insight for how you came up with the final problem, and particularly your property of hi of xi equal to 1 for all I.
Thanks. So this problem itself is inspired by some lattice problems called SIS problem. So that is to find, the problem is to find some element. So the first condition is same. You have to find a vector x that satisfies two properties simultaneously. The first is that belongs to some linear space, and the second condition is that each xi should have short absolute value, and that is a small absolute value. And that is the SIS problem. And as I already mentioned, so our this trick is inspired by Rege's idea, and this Rege's original work was about reduction from the LW problem to the SIS problem, which I just mentioned, and so our problem is inspired from that Ratch's problems. But we modify the condition, the second condition, by using the hash function.
Okay, thanks for your nice talk. And your quantum algorithm can find a state of superposition, which is a superposition of all the code words that satisfy the property. So is it possible to find some deterministic, somewhat specific code in with quantum algorithm?
Sorry, could you repeat that again?
Can we find a deterministic specific code word with quantum algorithm?
Okay, so you mean that we can only find the uniform superposition of
Yes.
code words that satisfy 1 and 2? Yeah, so the proof of randomness means that we cannot do that deterministically. So you cannot find a specific code word. So this procedure is inherently randomized, assuming that a conjecture is true.
Thank you.
So on one slide, you said that you wanted a linear code, but then on a later side, you're folding symbols together. So I'm not entirely sure what this means, but I'm going to guess that it means that you use a linear map to pass to a smaller finite field. So is this then the same as what are known as BCH codes?
Yeah, thanks. So actually, I omitted the detail, ignore the different that point. And actually, our code is not linear code because we fold. And so the point is that the folding operation is relevant only for analyzing the classical soundness. Soundness against classical computers. And for that part, it doesn't matter if the code is linear or not. And the linearity is only important for analyzing the quantum computers. Quantum algorithm. And for that part, the folding operation is not relevant. So when analyzing the completeness, when analyzing that the quantum algorithm works, we can ignore the folding operation and we can treat it as a linear code, and that's why this works.
Could you please comment a bit more on potential applications of your work outside complexity theory?
You mean the third one?
I mean, do you envision any other applications of this in other fields?
Other fields?
Like practical applications, for example?
So I don't have more insight than what you're raising here. I'm sorry for that.
So you mentioned cryptography?
Yeah, so for cryptography, so we already have implication about the separation between random worker model and quantum random model. Wait. This one. And so our result directly shows that these two models are different. And so this means that this, I can say that this has some sort of practical impact because the post-quantum crypto is a big deal in the real world. And usually we have to use quantum random walker model for analyzing this kind of post-quantum crypto. But sometimes some people still use the classical random walker model for analyzing the post-quantum crypto. But our result means that you actually need to use quantum random walker model, or otherwise your security proof doesn't work, may not work against quantum computer.
So given the time, we can have one last question, if any. So I guess not, right? Or
Thanks for the great talk. So my question is related to the first question exactly, I think. So usually when we like get tests of randomness, like a certification of randomness or whatever, so we have like, we define two observables that like we say they anti-commute somehow, like two observables belonging to the prover that like somehow anti-commute. And here, so the only thing that somehow makes sense is that if we add a layer of interaction and ask sometimes for a code word or a code word from the dual code, I was wondering if like there is any hope to go in that direction to try to establish two anti-commuting observables somehow.
Do you mean that is about verification?
Yes, or like
Yeah, so we don't have any concrete idea for that, and so simply because we have some, so the proof of the content protocol can control the behavior of the content computer, and that is the basis of the Mahadev's verifiable verification, and so this might be related to this, but we only have this kind of vague idea, and we don't have any concrete idea.
Okay, thanks.
Okay, so time's up. So let's thank Takashi again.